to introduce Shokfe Rathkar here today to give our seminar. So I know Shokfe again from EPFL. I met a lot of people there in my time. And yeah, Shokfe's work is very interesting to my group, but hopefully we can spread the word today of how you can combine photochemistry or photoelectrochemistry with scanning electrochemical microscopy and liquid-liquid interfaces to do some very, very nice work. So really looking forward to your talk, Shokfe, and over to you.
Yeah, thank you very much for your nice introduction. And yeah, welcome to my talk. First of all, I would like to thank Mihai for giving me this chance to have a talk in this very nice web series. And today I'm going to talk about the characterization of photochemical reactions at polarized liquid-liquid interfaces systems by using scanning electrochemical microscopy technique. So the works that I will present today were done during my postdoctoral career from 2015 to 2018. And Professor Gunther Wischlag Research Group at the University of Oldenburg, which is located in northwest of Germany, in very nice and calm city of Oldenburg. Actually, the works were supported by financially supported by two fellowships. Hans Wischerschaf's colleague is the Institute for Advanced Study and Alexander von Humboldt Foundation of Germany. So we all know that liquid-liquid interface is an interface between two immiscible electrolyte solutions that can be polarized and served as an electrode, similar as solid electrode. Such an interface enables not only to separate compounds due to their solubility, but also to control and monitor the transfer processes. So in this very nice scheme, you will find a variety of those transfer, which includes simply transfer of ions by its own energy, or so-called assisted ion transfer. These ions can transfer, for example, this metal cation with the help of ligand, which is typically located in organic phase. Another possibility is electron transfer between two immiscible mediators, which are located on both sides of the interface. And finally, photo-induced electron transfer between, in a case of photosynthesizer in one phase. So therefore, in this kind of interface, transfer of electron, ion, and neutral species can be combined in such a way to conduct the reactions, important reactions, such as energy-related reactions. However, this kind of interface has not been very progressed due to or compared to the solid contact. This is because of a lack of suitable tool in order to decouple these complex transfers. So one nice approach or possibility is the scanning electrochemical microscopy that we all know, that allows us to precisely position the microelectrode or even nanoelectrode very close to the interface in the scale of micrometer or nanometer, in order to locally probe the charge transfer at the same time to institute detect of the product of that reaction. And this is very helpful for us to get complementary information about the reactions which are still unknown in liquid-liquid interfaces systems. So one nice example here is proton-coupled electron transfer and oxygen reduction. In the presence of frozen derivatives, such as the commutative frozen with the abbreviation DMFC. This work goes back to Winsol's work in 2008, and Professor Géraud's research group, actually, and they explored this reaction and proposed a mechanism for that reaction. According to that, the proton is pumped into the organic phase by a potential drop, and that's actually followed by that transfer of homogeneous oxygen reduction take place with DMFC as an electron donor to produce hydrogen peroxide, which this product can be quickly extracted into the water phase. There are important points in this reaction. First of all, oxygen reduction selectively takes place in the organic phase, which is energetically more favorable than in water. Second, all the processes is controlled by galvanic potential difference. Please note that in this kind of interface, potential can be adjusted either electrochemically by using a potentiostat or chemically by dissolving common ion between two phases. Here, transfer of common ion can induce potential difference, which according to Nair-Stoneman equation depends on transfer potential of that common ion and its concentration in both phases. So third point is that this proton transfer play key roles in this reaction. Proton can transfer by its own alone or can be facilitated by proton phase transfer catalysts such as lithium that has been proposed by Deng in 2014 and Professor Giraud's research group. So actually that was my motivation in order to design experiment to answer the question that how does oxygen reduction reaction proceeds with alkaline cations without adding any proton into the aqueous phase. Therefore, we designed a simple two-electrode setup. So with the liquid-liquid interface, which was mechanically stabilized at tip of pipette, the pipette is filled with organic phase of BATB as superhydrophobic electrolyte, and with and without DMFC as a electron donor. So then this filled pipette was immersed into the aqueous electrode solution of lithium chloride, and in this case was lithium chloride, and then we added silver chloride as a working electrode inside the pipette, and another silver chloride as a combinatory auxiliary and reference electrode in the outer aqueous solution. Then we used actually these two electrodes to apply the potential at the interface, at the same time record cyclic voltammetry based on ion transfer. So in the right side, you see the background CV that we measured with only electrolyte in two phases. So here, the positive current is defined due to transfer cation from organic to water or an ion from water to organic. For the negative current, this actually direction is reverse. Therefore, according to the sign of the current and the shape of the response, which is peak or steady state, we found that this potential window is limited by transfer of chloride in positive side and lithium in negative side. By addition of the DMFC into the organic phase, you see that the negative current wave increases and the onset potential shifts to more positive potential. This wave is due to transfer of lithium from water to organic. In the back, actually the reverse scan, the peak shape response was actually disappears, and this peak is due to the back transfer of lithium from organic to water. So in general, this response shows irreversible transfer of lithium from water to organic. So then in the next step, actually, we measured background CVs for different alkaline or different aqueous electrolyte of chloride salt of different alkaline cation, and you find that negative limit shift to more negative potential by increasing the standard transfer potential of cation. For example, we have most negative limit for sodium chloride with highest transfer value for sodium, and we have least negative potential for potassium chloride with highest lowest transfer potential value for potassium. And with addition of DMFC into the organic phase in those systems, again, the irreversible transfer of cation for all those cases is evident from the CV result. But the problem is that from the CV we cannot get enough information to explain the irreversible transfer and to compare activity of different cations. Because of that, we decided to design a SECM in substrate generation and tip collection mode. So their liquid-liquid interface was at the tip of pipette and can be polarized electrochemically by using two electrode setup, as I mentioned before. So here the potential can drive transfer of cation into the aqueous phase or into the organic phase, into the pipette, which then it can enter into the reduction of oxygen with DMFC and produce hydrogen peroxide. And this product can transfer or diffuse to the aqueous phase, where this bias microelectrode is precisely positioned to detect that molecule using 3 electrode setup. So in our setup, as you can see in this scheme, We had electrochemical cell with transparent wall, and then we had pipette, which was fixed in the upper part of the cell, and the diameter of pipette was less than 100 micrometer, and microelectrode, which was aligned to the pipette and was fixed in the lower part of the cell, and two camera and X and Y direction, for example, to position, to actually monitor the position of pipette related to the microelectrode. And we had two potentials that work at the same time. One worked with two electrodes to apply potential at the interface, and another worked with 3 electrodes to detect the product of this reaction. Important step here is alignment of pipette related to the electrode. That's why I briefly explained that. First of all, pipette was placed roughly 100 micrometer above the electrode surface, and this bias pipette was moving, for example, in X direction over the electrode surface. At the same time, the current at the bias microelectrode was monitoring, and this response was obtained, for example, in X direction, which shows the maximum current due to the point where this pipette was exactly on the middle of over the middle of the electrode. And then we fixed the pipette here, and then we repeated the line scan in Y direction, and this volcanotype response was obtained. And again, this pipette was fixed in this point, maximum point in Y direction. And after these two steps, then we can measure the approach curve in Z direction and stop and fix the electrode, this pipette at any distance of electrode that we want. The interesting thing here is that if you see by overlaying these two volcanotypes, this overlap area was obtained, which is exactly the opening, the area of opening of pipette facing to the microelectrode. So after alignment, so we measured the approach curve for oxidation of hydrogen peroxide, while the pipette was biased at the potential value, this potential selected from ion transfer CV that I mentioned before. For example, in the case of lithium, we apply minus 0.65 in this special condition, and which is due to diffusion control transfer of lithium into the pipette. So here you find that the oxidation current increasing by approaching to the interface. This is because of the higher amount of hydrogen peroxide near to the interface. That remarks the interface as a local source of hydrogen peroxide. When no potential apply at the interface, so you see that the current change is almost zero. We also apply our potential for all those cases. You see that the current changes are less than 5 picoamp, therefore they are negligible. So this blank experiment shows the necessity of lithium transfer to organic phase to facilitate oxygen reduction reaction, but how this transfer can increase reduction of oxygen. So Link proposed a mechanism for that reaction. So hydrated lithium are the species who transfer to the organic phase, and their lithium can behave like Lewis acid to transfer proton to DMFC and produce a protonated DMFC complex. And this complex, the next step can react with oxygen to produce superoxide radicals. And this radical in the next step can react with another molecule of DMFC and hydrated lithium to produce hydrogen peroxide and lithium hydroxide. And these two species finally partition into the water phase. Therefore, the lithium get back to the water, and they believe that it plays a role as a proton phase transfer catalyst for reduction of oxygen. In order to compare the activity of different alkaline cation, so we recorded the approach curve based on oxidation of hydrogen peroxide for different alkaline cation, and you find that the oxidation current increases in a clear trend with maximum current for lithium chloride and minimum for potassium chloride. Different responses must originate from different generation rate for hydrogen peroxide, and that must originate from different alkaline cation which transfer to the organic phase. And if we look more carefully to the trend, we see that this trend is exactly the same as the sequence, the acidity sequence of those cations. So that's therefore we sampled the current from approach graph, for example, at 2 micrometer distance between pipette and electrode, and then we plot those currents versus the hydration energy of alkaline cation, which are known from literatures. So we ended up with this linear response, which tells us that cation with higher hydration energy, therefore higher acidity, can show higher catalytic activity for oxygen reduction and therefore higher rate for generation of hydrogen peroxides. So this confirms the role of hydration shell and surprising acidity of alkaline cation for reduction of oxygen, and approved the proposed mechanism for that catalytic reaction. And by extrapolating of this line, also we predicted a rate of oxygen reduction for the cases of rubidium and cesium as the other cations of this group. So as a conclusion of this part, I have shown you that how we can design a SECM for characterization of oxygen reduction reaction of liquid-liquid interface. And our results showed that the catalytic activity of alkaline cation and compare their activity, and also the result approved the mechanism for selectively production of hydrogen peroxide, the presence of hydrated alkaline as a proton phase transfer catalyst. As an outlook, one can think to use the same kind of setup to study of oxygen reduction, the presence of other cations, for example, magnesium or aluminum. Since they have higher charge density, one should believe that they could have higher catalytic activity for oxygen reduction compared to alkaline cations. Or ammonium, we all know it as a typical and classical proton phase transfer catalyst. So in other words, we use liquid-liquid interface. Actually, we all know it as a unique and flexible and defect-free substrate for assembly of nanoparticles. For example, bismuth vanadate nanoparticle, which in our work was as a semiconductor photocatalyst for oxidation of water. So we started with aqueous electrolyte solution with nanoparticle dispersed in it. We add organic phase on top of this. And this interface was quickly formed, and transfer of common ion. So this built up potential difference between two phases, and that's pushed negatively charged nanoparticles into the interface and form uniform layers of bismuth vanadate at interface, as you can see here in this photograph. So finally, in the presence of light, this form can generate electron and holes, which can be separated from each other, quickly accessible for photochemical reactions on both sides of interface. In the first experiment, actually, we wanted to check the possibility of electron transfer between bismuth vanadate at the interface and the organic mediator, which here was the bipyridine cobalt complex. So a SECM setup was designed with microelectrode, in this case gold microelectrode, which was located in organic phase and close to the interface, for example, here 20 micrometer. And then the electrode was biased for detection of the product of this reaction, which here in this case is reduced form of cobalt complex. Therefore, transient based on oxidation of cobalt was measured under light pulses. Then the current in the presence of the light here shows or confirms the transfer of electron from conduction bond of bismuth vanadate into the organic phase where we have this cobalt complex. This here I should mention that we selected tetrabutylammonium as a potential determined ion for this system. So the photocurrent responses were measured under different conditions, for example, different pH of aqueous solution. So you find here that the current increases from acidic to the basic solution. We should know here that the driving force of this photo-induced electron transfer is determined by two terms. First is galvanic potential difference, as I mentioned before, is controlled by common ion and Nairstone and nucleation. Another term is the thermodynamically energy difference between electron transfer potential of cobalt and energy level of conduction band of bismuth vanadate. As you can see here in this energy diagram, by increasing the pH, on one hand, the energy level of cobalt complex doesn't change, and on the other hand, the conduction band of bismuth vanadate shift to more negative potential. Therefore, this energy difference between these two species increases, and that's increased the driving force of electron transfer and resulting current. Another direction condition, the response increases actually with tetrahexylammonium as a common cation compared to tetrabutylammonium. So this maybe because of this tetrahexylammonium is more hydrophobic cation, and that can induce or establish more positive potential at the interface relative to the organic side, and that's increased the driving force of electron transfer and the resulting current. Yeah. Now, we were interested to study the kinetic of that electron transfer reaction in the presence of the light. In the case of perchlorate as a potential determining ions. So the SECM setup in feedback mode was designed, and the approach curve based on oxidation of cobalt as a mediator in the organic phase were measured under different concentration of perchlorate in aqueous phase, while its concentration in organic phase was fixed and doesn't change. So for recording of those curves, this biased microelectrode was moving from organic side into the interface. Close to the interface, the oxidized form of cobalt diffused to the interface where it can get electron from bismuth vanadate and regenerate the initial form of cobalt complex. And this species then diffuse back to the electrode surface where they can get oxidized again and complete a loop and provide the positive feedback the electrode surface. Therefore, in the approach curve, you see that the oxidation current increases close to the interface, and you find relatively more positive feedback for lower concentration of perchlorate in aqueous phase. So those approach curves were fitted according to the model of Conrad and Lafroy, and from that we obtained kappa, the apparent electron transfer rate constant, which those values are or can be correlated to the effective heterogeneous electron transfer constant or K effective according to this equation with the known value of diffusion coefficient of cobalt complex as a mediator. So then those values for K effective were obtained, and we plot ln K effective versus driving force. This linear response was obtained, which tells us that by increasing the driving force, the K effective increases. And this line was fitted by this Butler-Volmer equation. So from this slope and the intercept of this line, we extracted the kinetic parameters, for example, the K0 and alpha. In conclusion of this part, actually, by decreasing concentration of perchlorate in aqueous phase or applying more positive potential at interface relative to the organic side, we can obtain higher K effective value for electron transfer reaction at the interface, and therefore we should expect faster electron transfer between bismuth vanadate, photocatalyst at the interface, and cobalt complex as a mediator in the presence of light, of course. So then the approach curve for, in the next experiment, the approach curve for oxidation of cobalt were measured again, but this time for different concentration of cobalt. And you find here that the relatively more positive feedback can be obtained for lower concentration of cobalt. By fitting of those approach curve, K effective value were obtained, And by plotting of reciprocal of Chi effective versus the concentration of cobalt, the linear response was obtained, which tells us that by decreasing the concentration of cobalt in organic phase, the Chi effective is increasing. So this line was fitted into this equation that we derived from the similar equation in dye-sensitized solar cell. Despite of different mechanism, but those systems have the same response. And this formula, Chi effective describe, actually this formula described the relationship between Chi effective and concentration of mediator, and also regeneration rate constants of the mediator. Here we should consider that Chi effective is strongly also influenced by electron-hole recombination and also ability of the system to absorb the light. So these two parameters also should be considered and should be inserted in this formula. Then we repeated this approach curves for different concentration of perchlorate, and we obtained different linear response for different concentration. In general, we found that the Chi effective is increasing by decreasing in perchlorate concentration, and also lower intercept was obtained, which reflect a higher regeneration rate constant for mediator. In conclusion, if we decrease the concentration of the concentration of cobalt in the organic phase as a mediator, then we should expect faster electron transfer between bismuth and cobalt in the presence of the light. So what's happening on the other side of interface where we have the water? So in principle, the water molecule should be oxidized with photogenerated holes and produce oxygen as a main product. And those species which are generated in the water phase diffuse through the porous layers of bismuth vanadate into the interface in the organic side, where this bias microelectrode is approaching to. So this approach curve based on reduction of current tells us that the reduction current increases by at close to the interface. This remarks the interface as a local source of oxygen. And here we see in the blank experiment without any light, the current change is almost zero near to the interface. You also find that the reduction current increases by decreasing concentration of perchlorate in aqueous phase. So as a complementary experiment, we fixed electrode at a close distance to the interface, for example, 5 micrometer in this case, and then we recorded the transient based on oxidation of oxygen and under light pulses, and you see that the photocurrent here confirms the generation of oxygen in the presence of light and bismuth vanadate. And also the result shows that the reduction current increases by decreasing in concentration of perchlorate. And this is because of the higher amount of oxygen that can be generated by applying more positive potential at the interface now relative to the organic side. And that may originate from three parameters. First, increasing in driving force of water oxidation. Second, increasing in amount of photogenerated holes which are accessible for oxidation reaction. And third, increasing in coverage of bismuth vanadate who are adsorbed at the interface. But the coupling of contribution of this effect actually in overall water oxidation to generate oxygen, that can be interesting target for the next and future experiments. But on the other hand, water oxidation is a very complicated four electron and four proton transfer. It may include some radical intermediate besides oxygen as a main product. So therefore, in order to quantitative assessment of those radicals, we design a SECM setup in surface integration mode. In our setup, bismuth vanadate was fixed or was stabilized at tip of pipette and was served as a photosensitive substrate to generate hydroxide radicals, for example, during oxidation of water. So in our setup, this pipette with nanoparticles was fixed on the upper part of the cell, and the other side it's connected to the optical fiber, and the outer wall of the pipette was covered with ink, with silver ink, and thanks to this special design, pipette can serve as a light guide and direct and concentrate light at the end of the pipette where this bismuth vanadate was settled. And then microelectrode was aligned the lower part of the cell, and reference electrode and auxiliary fixed from the side into the cell, and camera was also fixed in the front of the cell in order to monitor the position of pipette related to the microelectrode. So then the principle of this experiment is shown in this scheme. So you see that the reduced form of mediator can be generated at the electrode surface, and those species can diffuse to the pipette where they can react chemically with hydroxide radical which are adsorbed on the bismuth vanadate and regenerate the initial form of mediator, and those species then diffuse back to the microelectrode surface and increase the reduction current and support positive feedback. And this loop can be repeated until all these adsorbed radical can be consumed during titration reactions. So then this increasing in the reduction current and the microelectrode can be correlated to the amount of radicals which are generated during photooxidation of water and are adsorbed at the bismuth vanadate surface. So SECM software actually was developed for this particular experiment by Professor Wishtag, and he, in order to add possibility to define and apply the sequences of light and potential over time. That's program. Initial multi-steps. First of all, it includes initial step where the microelectrode was biased at a reduction of mediator, and here we don't have any titration reaction, therefore the current at the microelectrode surface is due to hinder diffusion of mediator species into the electrode surface. And here we only can record the background transient. Then we have illumination step, so where generation of a radical take place, and mainly the radical, mainly I would say hydroxide radical, which can be generated can be generated and absorbed at the bismuth vanadate surface, and the electrode here biased at open circuit potential. And then we have a delay step. Electrode still has OCP, and the radicals may decay during some side reactions. Finally, we have integration step, where the electrode was biased, can be biased again for reduction of mediator, and the titration reaction take place between reduced form of mediator and hydroxide radicals. And here we can measure titration transient according to the reduction of mediator. Compared to the background transient, reduction current increases. So if we subtract these two transient and integrate over time, the consumed charge can be obtained, which is the density, coverage density of adsorbed radicals, which are generated or which can be generated during photooxidation of water. So then these titration transient were measured under different delay time. You see here that the reduction current increases by decreasing in delay time. So this is expected because more radicals decay at longer delay time. So if we assume that recombination of radicals, hydroxide radical to produce hydrogen peroxide is a main side reaction and it's follow second order, then we ended up with this equation by plotting of reciprocal of coverage density of radicals versus to delay time, we ended up with this linear response, which from the slope and intercept of that line can extract the kinetics related to decay of those radicals. First, the coverage density of those hydroxide radicals can be obtained, and second, the decay constant of those radicals. So in conclusion of this talk, actually, SECM, I have shown you SECM in different working mode and different configuration that can be integrated into liquid-liquid interface system to characterize the photoactivity of nanoparticles without generating solid contacts. And I have shown you that chemical polarization by common ion can facilitate charge separation, and that can influence the rate of involved reactions of electron and holes on both sides of interface. And formation and decay of those radicals, intermediate actually during photooxidation of water, can be quantified by surface integration mode of SECM. And the interesting thing here is that the value that we obtained, the quantity value that we obtained in this experiment, actually was very in good agreement with the reported values in the photocatalyst, in the same photocatalyst, but in the solid contacts. As outlook, one can think to design of Z-scheme photocatalyst system for overall water splitting. So here, one liquid-liquid interface with oxygen evolution photocatalyst can be combined with another liquid-liquid interface with hydrogen evolution photocatalyst with a common organic phase in the middle, which contains the redox mediator. Then regeneration of mediator in both sides can relay electron from oxygen evolution part into the another part to generate hydrogen. So as I demonstrated in this talk, and as a general message of this talk, SECM approach actually can be simply integrated into this system in order to systematically optimize and study and optimize this function of this system for overall water splitting, respect to the choice of materials for photocatalyst on both interfaces, or the electrolytes, for example, this water electrolytes on both sides, and organic electrolyte, and also the type of mediators. Yeah, thank you for your attention. That's it.
Thanks so much, Shokve. Inspiring talk. Loved it. Really, really great. Fantastic presentation with beautiful cartoons to highlight very complicated work you're actually looking at with the SECM. So I'll stop sharing your screen and I'll open it up to